Oh, great. All right. Well, welcome everyone. My name is Mark Hofer. For those who don't know me, I'm so happy that you're all here, and those, I guess I should go here. Oh, and those online. That's kind of strange. I think I'll face the real audience, the physical audience here. But this has been a long time coming. The organizers, who are Michael Shearer, Girotti L, Antonio Moro, and Barbara Bernari, who's not here yet, she'll be here next week. We all kind of got together and decided to do this 5 years ago. It's when we first nucleated the idea. So we put in the application, and we're really happy that it's finally coming together. And this is the very first seminar of the research program, the 6-month program. And so I just wanted to give a few kind of opening remarks, just to kind of set the stage, and also for the folks online who will be coming, many of you will be coming later, what you get to anticipate. The first thing is the program is divided up into 4 themes. The first theme, which is happening now, is modulation theory. Each one, and DSWs, each one occurs for about a month and a half. So July and August has modulation theory and DSWs. The next one is analysis of dispersive systems, and that's going to be August, September timeframe. And then we move into random phenomena and soliton gases in October and November. And finally, we conclude with physical applications in November. Well, each of these is the themes, and there are 5 workshops. So Girotti mentioned workshops. So we have 5, and 2 of them occur during the analysis theme. One is here in person at the Institute, and then the one that comes right after it is actually in Loughborough. So those who are visiting the program, we're going to be having a bus to go down to the workshop, and we'll be residing there for that satellite workshop. So as program participants, we hope that you'll be inspired to engage in, well, certainly lots of fun together, collaborations, new and old. Seminars like this one, which I'm really happy to have Professor Tamara Grava being the first one. And we're planning to have 1 to 2 seminars per week outside of workshop periods. And we have some special events planned, which will be communicated to you all, as well as the workshops, the first one being next week. And of course, there'll be discussions, the blackboards, and lots of social opportunities, since we're all here together. And for many of us, including myself, this is our first time getting together with colleagues in many years. So really excited for this opportunity. And all of us organizers welcome any suggestions or recommendations for things we could do, program structure, and so on. So we invite you to come talk to us at any time and let us know what you think, and if you have any ideas. And I'm especially keen to learn more about the virtual experience for those who are online, because we've been mostly focused on the folks that are here. And so we welcome any feedback on how the virtual experience can be made more enticing, I guess. And just on a weekly basis, I understand that on every Monday, an email is sent out with the schedule for the week. That comes from the INI staff. And now and then you'll be getting emails from the organizers as well. Okay. Also, participation is in flux. People are changing their dates and so on. And so we really hope that you'll communicate if you have any changes to your dates, if you know you're not going to be here when you've signed up to be here. And similarly, if you'd like to possibly add more time, reach out to the staff, reach out to the organizers, and we'll see what we can do to accommodate that. And I guess with that, those are the only opening remarks. I'm really thrilled to be here. And so for our first seminar, I'm going to invite my co-organizer, Girotti L, to introduce the speaker.
Okay, thank you very much, Mark. And it's a pleasure to introduce our first speaker, Professor Tamara Grava from CISA, Trieste, University of Bristol, are so many fundamental contributions to integrable systems, solitons, animation theory, orthogonal polynomials, statistical that you just named there. So today she will talk about soliton versus soliton gas. The stage is yours.
Okay, thank you very much. I mean, I'm starting my introduction. And first of all, I want to thank on behalf of everybody here for the huge effort you have done to put this semester together. And so far, it's starting great. We have signed on everything. So it's really great. And I'm pretty sure everybody will benefit most of the things, at least this summer here. Okay, so what I'm talking about is okay, so something's going on with a bunch of people that are coming here, and probably you will hear, I mean, Manuela, Marco, Alexander, Bob Jenkins, McLaughlin, and Giuseppe, they all come here probably in some different form. You will hear this stuff again. So if you don't understand on the first go, you have a chance to understand on the second. Okay, so I will talk about we have been starting to study with Ken and Manuel and Jenkins. Soliton solution of integrable equation with infinite number of solitons. We study analytical process for this kind of solution. So which kind of solution do we get? So this is the main thing. And so why do this? Well, I mean, solitons are fundamental solutions. So the natural question is when you have a lot of them, which kind of solution you have, which are the property of this solution. And so the first part is to describe the behavior of large set of soliton solutions. So what is a natural way of doing this? And the second part is to put a big soliton in this gas or soliton to see what's happening. So what is the happening? And so if we do this, what we get is a kind of soliton kinetic equation, which is which I explain in a bit what it's going to be. And so I will focus on two equations, modify KDB and the nonlinear shear. Okay, so let me give some history about this. This is starting in a paper of Dakar, 1971, where he considered the interaction of what we call dilute gases of solitons. So in observation, what everybody knows is that if we prepare two solitons, which are this expression at this should be T minus infinity, when they interact after interaction, so the eta2 here, so we have two solitons with two different amplitudes, eta1 and eta2 squared. So and eta2 is bigger than eta1. So if you prepare them in this way at minus infinity, or at T minus infinity, so when we go to look at what happens at plus infinity, the shape of the soliton is unchanged, and the only difference is the phase shift. One is positive, one is negative. So that's what is happening. And this phase shift is as this logarithmic expression. So the idea of Zakar was, okay, what happens if I can consider, I mean, the paper is very vague. I mean, I spent a lot of time on it without understanding much. But I mean, so he introduced this concept of soliton density, which means let's have this quantity rho of eta. Eta is the spectral parameter in the spectral sense. In the sense that this quantity, if you multiply it by d eta, dx, and dt, is the number of solitons which are located at the distance dx, time dt, and we come to beta. And then you launch a tracer soliton, bigger soliton in this gas, and you want to know what is the velocity of this soliton. Okay, and its claim is that the velocity of the tracer soliton is equal to the free velocity. So this is for eta squared. So it is supposed to have soliton quantity theta plus an interaction term, which is this non-local interaction. And then, so this is an integral. So this is this integral term, and this term comes straight from so it's inspired by this logarithmic equation that is coming from the study of soliton. And then there is a continuity equation for the density. Okay, this equation, I mean, probably attract the attention of Genadiel, 20 years, 30 years later. We try to understand a little bit more about this equation, and different perspective. So he studied the limit of finite gap integration in the limit when in the solitonic limit. So infinite soliton, infinite finite gap, but in the solitonic limit. Then he was able to extract this integral equation. So this is correcting Zakharov equation. So this is for density, for a dense gas of soliton. So before this quantity were approximated by eta square, and now we have the velocity. So now this is what is called the kinetic equation for a soliton gas. So we have the density, the conservation of the density, and the velocity. And this is just to compare. So this is kind of these are interesting equations in the sense that I mean, if you compare with all your equations, so you have the conservation of the density that is zero, but the velocity certainly is given again by a conservation over this is the pressure. Well, here in this, so you can think really of a gas, but where the velocity term satisfies this integral equation. So this is a different, so it's a different object that is an interesting object. Okay, these equations that were extended in several directions. So there was the work of Pelikan Chacton and told this, and then I mean there are also a lot of numerical works with a lot of soliton done by Kalinowski and Shurgalina and Kalinowski and Gurwitz and many others. I'm not complete here. So what I want to do in this talk is to just to obtain this kind of equation for in the analysis of Cauchy problem for modified KdV when we put a lot of soliton. So this will be a kind of deterministic setting. While here so these equations are deriving as also for random setting. So this is this row represents a sort of soliton density. If you expect your soliton to be a random object with this probability distribution, this row represents the probability distribution of the soliton. Okay, so this is the setting. So now let me say a few words about solution with infinite number of solitons. So the first times that this was being considered is in this by Peter Lacks and Evermore when they studied the small dispersion limit of KdV with initial data such that the reflection coefficient is basically zero exponential. When you send this epsilon goes to zero, then you arrive to infinite soliton component. And this infinite soliton component drives the dynamic of the solution. Then there was this observation by Zaitsev, Nitan, and also Boyd. So there are three different works where they show that if you sum the section and shift it by n, so you do an infinite sum of sections shifted by n, so this n is an integer, then this is an elliptic solution of KdV. So this is it's all only for such. So if you try to do the same gymnastic with two different sections, you won't get the Jenkins solution. That's not possible. So you don't get if you try to do this exercise, you don't have to
What is sigma here?
Sigma is a parameter. Yeah, it's just a parameter.
Period.
Period. Yeah, that's the parameter. It's the period you're shifting. Okay, so then there was some paper in 1992. This is a little bit formal of by Gzeski, Karlovsky, and Zhao. And there are many. It's not only one. There are many papers about this subject where they study soliton for KdV, and they basically these are mostly existent theorems. So which condition you have to put to the eigenvalue? So this now I call kappa j. And the norming constant of each soliton to get a convergent solution. So this is our condition on how this eigenvalue and norming constant of the soliton have to be in order to converge and proper solution. It's mostly to do on its system results. And so then I mean maybe I'm skipping some in between this probably 92 and 2021. Maybe there are some other stuff in between. But then, I mean, we studied with Manuela, Bob Jenkins, and McLaughlin an infinite soliton limit for KDV, and this motivation was so we have been attracted by a particular solution of the Jenkins Sakharov that they introduced new solution of KDV that they call primitive potential, and they are constructed to an local number problem. So the motivation, so okay, they described the solution very hard, so difficult to study, but we obtain in a particular case of their primitive potential a solution of KDV, which can be considered an infinite soliton. So this is what we do. And here, so what I want to present is a construction which is inspired by this work of the previous work with Comm for modified KDV and NLS. So this is what I'm going to show today. And Manuela in two weeks will present more details on the modified KDV case, and probably Marco or Giuseppe will present NLS in more detail. Okay, so that's the problem. So let me say a few words about modified KDV. There are two elementary solutions that are traveling waves. So the localized traveling wave is the soliton. And for modified KDV, we have so the soliton is characterized by its velocity, its amplitude, kappa, and also by this norming constant, which I call chi. And according to the sign of this norming constant, you can have a positive or a negative soliton, and in modified KDV, admit soliton and anti-soliton. So both positive and negative amplitude. And this norming constant chi is so the position, so the peak of the soliton at time 0 is located at x0. And so when you make this norming constant very big or goes to infinity, you see that x0 goes to minus infinity. So it means that when chi becomes very big or very small, you are moving the peak of the soliton to a plus or minus infinity. Okay. So just an observation. So we did this. So we are studying soliton. A solution of modified KDV with an infinite number of soliton on a zero background. But since this equation is not Galilean invariant, you can do the same gymnastic with an infinite number of soliton on constant background. Okay, so this is as far as soliton is concerned. And the other localized traveling wave solution is the periodic one, which is expressed to Jacobi elliptic function. And this is the one I'm considering. There's some paper of Pelinowski and which are also the other solution, which is expressed through the CN elliptic function, but this is the one I'm going to use here. So this is the Jacobi elliptic function of modulus m, and this is the velocity of the phase velocity of the traveling wave, and A is the amplitude. Okay, so these are the two solutions I'm going to speak about. So what will be the main ingredient of my talk? Okay, so now let me
Tamara,
yeah.
are you talking about the focusing in KDV here?
This is focusing, yes, sorry, I forgot to say, plus,
Yes.
plus, everything is plus, so everything is focusing on 524. Yes, both equations have the focusing, so we have the minus and minus, yes, but we are speaking about plus in both cases. Even because, yes, you don't have solitons, white solitons, in the focusing case. Okay, so now let me say how the solution. So these are integrable equations. So I'm not saying much in this term about integrability. Lax pair. So this can be solved by a lax pair. So we have a linear problem, and these are for both focusing modified KDV and focusing nonlinear Schrödinger equation. The lax pair is not a self-adjoint operator, so the spectrum is complex. It's definitely linear. So what we have here, so the n soliton solution is characterized by a discrete spectrum, so which is I kappa 1 and kappa n, and this kappa are here. So there are points on the imaginary axis and it's complex conjugate, and to each point on the discrete spectrum we have the norming constant kappa t1 tn. And in this case I'm taking well, kappa are up to be positive because you have to consider the complex conjugate, so you have negative, but this this Kj can be both positive and negative because you can have soliton and soliton. But what I'm going to do here is to take them all positive. If you take a mixture, it's a little bit delicate, and we actually are not able to do that. So if you take mixture of positive and negative, soliton and soliton, we are not able to do that. Okay, so so how is the n soliton solution obtained? Well, you construct this matrix HAL, which is as these entries here. So the square root of the kappa j and L divided by the eigenvalue, and then we have this phase. So the phase is well, this expression where you contain the time t and the space x in this combination with kappa. And here theta j means theta evaluated at I kappa j. Okay, so this is the matrix you build. And then the n soliton solution of the modified KdV equation is given by this difference of two log determinants. Okay, so actually this expression is not contained in this paper. I mean, so we derive it independently. There is the expression for q square. So yeah, the expression for q square. Okay, this is what we have, and then we want to send n to infinity. So how to make sense of this expression when n goes to infinity. So this is the goal. And okay, so you have to make some assumption of how you make n goes to infinity. Because how we make the number of solitons goes to infinity. So we assume that the point spectrum is the kappa are distributed uniformly on an interval, I eta 1 and eta 2. So we put an infinite number of solitons uniformly distributed on an interval in the complex plane. And then to have convergence, we need to rescale the coefficients. So the kappa j, chi j equal to chi j of the rank. And this is up to be discretization of a function. So we take this R, which is smooth, sufficiently nice, and so the kappa are simply the evaluation of this function at some point of the spectrum I kappa j. And now you understand why I want the kappa to be all positive or all negative, because if I have a mixture, I cannot get here a nice function. It will be a horrible function. If you leave this kappa oscillate while you are putting here, you cannot really almost function each other. So you cannot get R to be a nice function. Anyway, so this R will be real value positive and vanishing function. Okay, then after you do this, so you have to do some more gymnastics, but then for x and t in compact sets, you have always, when we send n to infinity, we can only look at the finite region of the xt plane. So you have to fix xt as big as you want, but in compact set, and then send n to infinity. Then this matrix, so the matrix that define these, so the matrix with which you define the n soliton solution, I mean, this is not so the determinant. So the solution was the determinant of 1 plus IA and so on. So so this matrix here become an operator with kernel given by this expression. Okay, so now you see the chi has to replace by R, and the kappa to replace by K and Z, where, oh, sorry, this should be W. So this W should be W and Z are in the interval sigma, which is where I have the eigenvalue. So this is done. Okay, so this is, so you have this matrix, I mean, this arrow means here that, I mean, it's not that this object converges to this, but the operator converges. So we have a determinant that converges to a Fredel determinant. So now the next slide, I hope will be clear. So what you have, what is really happening is that the n times n determinant in the limit n goes to infinity becomes a Fredel determinant. Okay. And so the solution, now we have a Fredel determinant. So now the solution before here, we have identity plus A and plus IA, identity minus IA. Now this has become an operator, kappa, which is an integral operator with the kernel kappa that I was given above. Okay, so let me go back. So this kappa is exactly this kappa here. So this is how things work. So you have this solution. So a finite determinant. So a finite determinant becomes a Fredel determinant, and this is just the definition of Fredel determinant. So it's the determinant. So we start with identity plus this infinite sum. Okay, so this is the determinant. You take kappa, this operator, you evaluate a different point, you calculate the determinant, and then you integrate between one dz1 and dzn. And so this is a n times n integral, so we have to integrate over the integral here. Okay, so this is the object. So this is what is happening. And okay, so this kind of solution. Well, Fredon determinant solution of integrable equation are known since the work of Dyson. Actually, Dyson was the first to write solution of KDV as a Fredon determinant, but they already appear in the literature. And actually, for the focusing modify KDV appear in a work of Tracy Widom in 1996. He was studying the focusing modify KDV and Saint Gordon. And he wrote basically a formula identical to this with only the kernel slightly different. And the interesting for us is that they also emerge, I mean, similar kind, but very, very close solution to this form. They emerge in recent literature for the focusing, again, for the focusing, modified KDV, in the study of fluctuation in random matrices, and in KPZ, so Cardar, Parisian, Zang, universality class. So in particular, this work here, I mean, here, a level of Kraj and Ledusal, basically they build very, very general set of solution for the focusing modified KDV. We are afraid of determinant which are similar to this case. And they are, I mean, they are the applications. That is a family of application. Okay. So now we have this formula, which is very formal, what to do with it, what it is in concrete terms, or what to look at it. Okay, as a Fredon determinant, I'm not able to do much, but you can always pass from a Fredon determinant to a Riemann problem, and this is more familiar setting. So an equivalent formulation is okay. So we have. We have a number of soliton in an interval, and we find the number of soliton goes to infinity. What is the Riemann-Hilbert problem? So associated. So what is the inverse problem? So Riemann-Hilbert problem is the inverse problem associated to this solution. Okay, the Riemann-Hilbert problem is the following, and it's very simple. So you assume, so this is the complex plane, spectral plane. And so the construction is the following. We want to find a 2 times 2 matrix meromorphic in kappa minus these two intervals sigma 1 and sigma 2, these two intervals here. And so that is going to 1 at infinity, and it satisfies this jump condition on these two intervals, sigma 1 and sigma 2. And so the jumps here are very simple. So this R is this interpolating coefficient for the norming constant, and here is the R bar. So this is the Riemann-Hilbert problem, and the solution of modified KDV is obtained by this expression. So you take the 1-2 entry of the solution, and you evaluate the limit at infinity multiply. So the 1 over k terms of the limit at infinity. So this is solved modified KDV. Okay, so this is the problem, how to find property of the solution. Okay, now we have the machinery. So there is a machinery that is large. So we want to first.
Can I have a short question before you go to the machinery? So here you have this upper lower triangular structure of Jack matrices. So what on the side of the Verhoeven determinant corresponds to this triangular?
There is solvent. So basically, these are the structure of this integrable operator of its. So, but it's the resolvent of the triangle. Correct? Yeah, exactly. That's why you connect.
Okay.
Yeah.
So it's this kernel K that you all should be on this guy.
Yeah, that's the same structure. But maybe just thank you for commenting this. Yes, in this recent literature of Kraj and Ledusal, but also Boltzmann that I forgot to mention, they are able to associate non-triangular. Actually, they're introducing more general solution where the Riemann-Hilbert problem does not have the triangular structure. So they go beyond the Girotti, etc. theory.
Or-
Thomas Botner, and then this paper that I mentioned, Krajenbrick and the Dusant. So it's a bigger class of solutions. Okay, so but this is I mean can be studied, and so what is the property of this solution? So the first step to do, okay, so you want to solve this problem, and what you have here? Here you have a term that is highly oscillatory, so you want to kill it or to transform in such a way you get exponentially big or exponentially small term, and you can give exact solution, so you are able to solve exactly the problem. Okay, so the first transformation that you need to do, well, you introduce two function, one is f, that is unknown and will be fixed later, and for us it's not important, and one function g. And the function g is probably a familiar object to you, so is this integral transform, so it's the logarithm of kappa minus s, so where this rho, this density now, well, is given by this expression. So basically, the first term represent an abelian differential of the second kind with polar to infinity, and this term with containing x, so we have t and x. So this first term is an abelian differential of the second kind with polar for the flat infinity, and this is of the first kind. It always have polar to infinity, and it's normalized between eta1 and minus I eta1. And here alpha is a three parameter, which is running between eta1 and eta2. Okay, so and this constant here, C1, C0, and C2 are uniquely determined by imposing this condition. So this is the object, and we define a wave phase. Okay, doing this transformation on the matrix X, you have a new Riemann-Inverse problem for T. You can deform contour in such a way that you get hold of the exponentially small and exponentially big difference.
Got it.
Thank you.
How do I do this?
What is this f function f?
F is only coming into the phase, actually. The phase
So
of the-
it's like mild g function. Actually.
No, it's changing the phase of the solution. So it's the only effect you need it, but it's only having an effect on the phase, not on the phase. So, yeah. So
But you didn't specify.
it will be uniquely specified when it goes to topic analysis, but the effects of it is only in the phase of the solution without zero.
So
Yeah.
it's not the leading model. You can
No.
this. Okay.
Yeah. No. Okay, so with the limit we have done, so the solution it looks very simple. So so in this case at minus infinity, the solution is exponentially small. At time, not the solution, the initial data. At time t equals 0, the initial data is exponentially small at minus infinity, and it is asymptotically an elliptic solution of KDD, of modified KDD at plus infinity. So it's the exact elliptic function, and so I want to put here the 1 over x. And maybe another remark. So this is basically step like you have 0 and oscillation on one side, and so it's oscillatory up to order 1 over x.
Are you imposing this initial data?
No, this is the behavior of this the behavior of the solution of this problem.
So the solution converges to.
Yeah, but
But where was the choice? The row?
no, this is not chosen. This is given from topic analysis. So the only thing you give is an inverse
R.
vector form. R.
R. Okay.
R on the spectrum, where you have
Right.
the spectrum.
And so the R associated with this is what exactly?
The R is interpolating the norming constant. The norming constant of the solid.
You just chosen in a specific way.
Yeah, the R. So that's all I want to say. The R, so we give the spectrum. I'm choosing the spectrum to convert to fill uniformly some interval in the complex plane, in the complex spectral plane. And the norming constant are interpolating a smooth function. It has to be nice, otherwise I don't know what to do with asymptotic analysis.
So put one on the perturbation because it's very specific. Well, they are quite natural. I agree. So
do you have any motivation for these two distributions?
Well, we choose something. I mean,
Okay,
just to see what was
Okay,
the solution. You can choose something else. It's not.
Yeah, basically.
Yeah, we can choose. Yeah, well, just to start with.
Okay.
But there is another probably subtle remark here because this limit is done. So the infinite soliton limit is done when you look for xt compact. Xt compact is an n to infinity because what you're doing practically putting this Morgan constant and you're sending all the solitons. Now I'm taking, okay, I'm converging for xt compact, I'm converging to this solution given by this formula, or this solution to this inverse problem given to this formula. And now I'm taking, okay, let's take this as initial data of modified KDB. Which kind of initial data is it? That's the question. That's what I'm asking. And the initial data, you do your asymptotic analysis. This is probably Alex is familiar to this. You have to introduce always a differential, this kind of stuff. But this object may be familiar to you. Generally, so this is a second kind differential.
Yeah. For the momentum.
Yeah, exactly. So if you do this asymptotic analysis, you have to introduce this object. At t equals 0, you have step-like initial data, and in this case, for t bigger than 0, you have a refraction rate. So you have 0 oscillation to connecting with the refraction rate. And so the asymptotic description, okay, is for x over t less than for eta squared, which is the.
It's a reflection of the width equation.
Yeah.
Okay.
Yeah. So for you have 4 eta 1 square. So for this one, you have q is exponentially smaller, while for x over t bigger than the trailing edge velocity, you have an elliptic modulated solution where alpha this is the modulation parameter. So alpha is a function of x over t, where when we are between these for eta 1 and 2, this V2 I will give you in the next slide. While for x bigger than over t bigger than V2, then alpha is just a constant. So this will be just an elliptic wave. And just I want to say always these are not exactly, but there is always an error. Okay, 1 over 4. So they are not exactly 1 over t, and here 1 over x. Okay, so this is what it looks like. Just to have the description. So we have a decay region, a modulated elliptic wave, and an elliptic wave. And so we have two velocity for eta 1, which is zeta is the slowest soliton. So this is the trailing edge. Then we have a modulated region, V2, where V2 is given by this explicit expression. You have kappa and E are complete elliptic integrals, and M is the modulus of the complete integral. So V2 is the velocity where you have modulation, then you have elliptic wave. Now what we do, okay, so we have this picture, and now I'm placing a bigger soliton inside this bar. And I want to study the dynamic of this soliton. So how does it behave? So this is the next goal. I put a big soliton and it should be big enough. You don't want so you want it sufficiently big. And I want to study the dynamic of this interaction. And so the result, okay, this is the picture which is very similar to the picture in the page of Newton. So you have a similar picture. So this is, I want to say, is not the solution, the numerical solution of this initial data, but the asymptotic solution. So the asymptotic solution.
Asymptotic for large XP.
Yeah. You are not able to solve the exact Cauchy problem, but they just reproduce the asymptotic solution. So asymptotic.
So it's a graph of the asymptotic solution rather than numerical simulations of game.
Yeah.
Okay.
But no, for the soliton, no, it's just yeah, but so we have two lines. One is the free soliton solution, and one is the real. So how it moves while interacts with this mass of solitons. Okay, so now to describe what's happening, let me introduce a few quantities. So I want to record that I have this G function, which is like the integral of this kind of abelian differential against this log interaction. And then I want to say this phase velocity, wave phase psi, which is the sum of G plus Kx and these two quantities. Okay, so just to say what is the meaning of this quantity, I want to say that rho ds for s going to infinity is exactly, so well, if you say rho of k decay for k goes to infinity gives like kx plus 4k cubed dx decay. Okay, so this is the. So I introduced to velocity one I call phase velocity, which is psi t over minus phi t over phi x, and the group's velocity is sort of t over x. Whereas this one. So this is basically the ratio of abelian differential, and there are two facts that so if I evaluate the phase velocity at I eta 1, then I'm getting the solution of the periodic wave, the elliptic wave, the end. And if I evaluate the phase velocity at I kappa 0, which is the big soliton, then I'm getting this expression where kappa is the first kind, complete integral of the first kind, and this is of the third kind. And this is, I call the average soliton velocity. And this quantity are also dependent on time, so they are time dependent to this, time and space dependent to this alpha. Okay, so what do this, so with this definition, so these are very natural. So this eta 1 square plus alpha, I want to point out, so it's up here, so it's exactly this quantity. So this is the velocity of the elliptic wave. Okay, so what do they satisfy? And then we have this soliton velocity. So what do they satisfy? It's just a calculation to show that they satisfy. So that the group velocity, so okay, now first the group velocity satisfy an integral equation. This is just by construction. So it satisfies this integral equation, and this has some resemblance with this Zakharov kinetic equation, and the soliton velocity also is satisfy an integral equation. So, and where here the group velocity is given by this ratio, and the density is the derivative with respect to x of derive. And this is, I mean, it's so this is for us was quite interesting. So this is satisfy kind of this integral equation that you get for soliton. And in this case, for this kind of solutions, so this continuity, so this rho as it is, it satisfies trivially the continuity. It's a trivial identity because of definition. So since V group is rho t over rho x, this equation is trivially satisfied. Okay. So basically, we were just saying that if I evaluate the soliton velocity, it satisfies in this soliton gas, it satisfies this integral.
Correct that you had minus the first one and plus the second one.
Oh no, it's not correct.
Yeah,
one of the
that's what I
two should
thought.
be minus. The soliton is positive, so it's plus.
Yes,
it was plus.
Okay.
Thank you. Misprint. Yeah, there are several. I know this, but okay. So
question: what is the difference between rho sub x and dx?
See,
So the kernel.
yeah. Sorry, just I described. So sorry, it's the same. Sorry. I'm not confused. I cut and paste from different.
Okay, so it's
From different
basically-
slides and different paper. Yes.
It's basically the same equation.
Yeah. The same equation, but no, it's group. So.
reason 12.
So this is this group velocity is just by construction satisfies this integral equation. But here we have the soliton speed. So we have this V, and it satisfies an integral equation
Yes.
by construction. Okay, so now let me.
What is the group velocity
Is rho t over.
need in this context?
This is in this context. I mean, for me, it's clear when I evaluate at eta 1 or eta 2 is is the Witten, the Witten speed, the speed of the Witten equation.
Which one?
Well, but so this is a ratio of abelian differential. So when you evaluate eta 1, you have the speed lambda 1. When you evaluate eta 2, you have the speed lambda 2. Now I'm not evaluating, I'm leaving it free, and I'm integrating between these two. I'm not evaluating a specific point. I'm leaving it. So this is ratio of the two abelian differential by which you define the Witten modulation equation.
if you chose a specific K, you could recover the limit velocity.
Yes, exactly. If you evaluate it at eta 1 or eta
But then
2,
the endpoint.
at the end points or the alpha, you
I
are
see,
doing.
right, got it. Okay.
But now I'm not evaluating.
Right.
And let it very continuous.
Right.
So, and this is, I mean, this is just, it comes quite in a quite straightforward way from this G function that is very common when we do asymptotic analysis with Riemann Hilbert problems. Okay, so
But what it represents, so what is the difference?
this is this, what I define is the V phase. Now I will explain what is this.
Okay.
Okay, so this is, I define like the average soliton velocity. Is it indeed the average soliton velocity? This is what you're asking. Okay, so the result, and I think Manuela will speak more about it, is the following. So we take the soliton sufficiently big so that when it interacts with the elliptic wave, there is always a single maximum. So you can always trace the maximum of the soliton. So you have to have it sufficiently big, otherwise when it interacts, you can have more than one maximum. So you can have maximum of the same height at the same time, but if you take it sufficiently big, you will have a single maximum. And then when you look at this peak, so I call this x peak of t the position of the maximum, which moves in time. So this is position of the soliton. And then this is the plot of the peak minus the position of the free soliton. So you just, and you see this is kind of step-like behavior. And this is the velocity of the peak when interact with the soliton gas. And you see it's highly oscillatory. Okay, so the statement, and this is a theorem, that if you calculate this quantity out of those initial data and you average over a period, so you average over a period, then you get this average soliton velocity plus correction of order 1 over t. And this period, of course, is a function of time because you can see it varies over oscillation. So here is plotted the velocity of the peak, which is highly oscillatory, and here is the average velocity.
So basically, incorrectly on the product about soliton moves or soliton gas, and because it interacts with each of the soliton, just
Yeah,
it's like this.
it's oscillated, so it does but the average is the soliton, and this is the start that satisfies the kinetic equation. The average velocity satisfies the kinetic. So that's the result. Okay, so this is actually all I want to say. Also, my time is also already over. Okay, I'm off part of my talk, but fine. So I want just to say some comments. So I mean, in this talk, so in this example, so many of the feature of a soliton gas in the presence of randomness seems to appear in this deterministic setting. So it's completely deterministic, and it's so that's the observation. So this is first observation. So for modified KDB, of course, other condensates are possible, like breeders. And so this is another thing that could be interesting. And then, of course, there is some on the numerical side. Yes, I would like to compare a Fredholm determinant solution, the exact solution, maybe using Bornemann algorithm with the large N solution. Okay, so maybe if I take, no, because I was going to speak about focusing on MS. I don't know if it's, I'm stop for, I need for my next talk. I don't know, how do you like? I will take probably 5 minutes over.
Okay, thank you. Thank you very much.
If I understand correctly, I want to return to this part in the Riemann-Hilbert problem. If I so not in the Riemann-Hilbert problem, in the setting, this is like this R is the so when you sample it, you get this phases. So it can be any smooth function that is positive. It cannot be zero, right? But otherwise, it can be any.
Yeah, it would be nice to interpret so to a positive negative, but then you don't know what.
Yeah, but at the moment but it can be any positive.
Yeah, if you do random, so when you want to do random, you need it random. So you will be have very rough initial data. And nobody is able to do asymptotic analysis for happening. So random soliton means this is random. That's,
Right. But it's still random, it's just you say it's positive, right? And it can nice, but otherwise it can be anything.
yeah, it's random or it's nice.
Nice random.
So you said there's this issue with the sign of R. But couldn't you just take 2n solitons and make -n to -1 R is negative?
Yeah, and then I can put some bunch of positive, a bunch of negative.
Yeah.
Yeah, then you get to choose 3, 4, you have to
I
increase.
see. So it's just adding more bands. It's not
Yeah.
actually changing. It's not, but will you be adding the anti-solitons?
Yeah, you will add in more bands, but then you have to add more bands because when our change sign is like opening, so you need to add more bands.
Sure about this. But I mean, you said when chi is negative,
Yeah.
you get an anti-soliton.
Yeah.
Right? So,
And the dynamics will be very rich because so when two soliton interact, they don't sum of amplitude, but when soliton and anti-soliton interact, the amplitude sum. So you have this is a model for in this paper of turning off tension. Then is a model like of increase of amplitude in the case of distribution of solution.
You can get some long waves.
Yeah, it's a model for Broadway because you have so when you have this part of soliton and anti-soliton, you will have very large peak, and it's I think it's very interesting to study. So this condensate of.
Well, as long as you deal with this solitons, before that you did similar analysis for the K.
Sorry?
Before this work, you did similar analysis.
Yeah.
For K. Are there any? Well, I understand. It's different scheduling, probably different black pairs. So, are there any quality differences?
No,
I understand that calculations are different.
not that this, no, because the cycling was very, so the qualitative difference that, okay, for the we put all the soliton on -infinity and 0 plus infinity, while here we put, so you can put all the soliton plus infinity or -infinity, so here in this case we get a fraction rate, just to make a difference. And another, so the difference, no, it will be difference if we start to put steps, right? Yeah, because Phys doesn't have, so you have some difference.
So,
Sorry, another difference that also has not been analyzed is when you put solitons, both are plus and minus infinity. So you want to see, so you have two different steps, but they are both considered plus and minus infinity.
So I mean, when you have the possibilities, it's from time asymptotic, and you get basically dispersive shock wave,
Yeah.
which is actually the solution solution in this case. It is dispersive shock wave between two levels of the same sign.
Yeah,
For the
because we built, well, for KDB was not, but we built it.
No, for
like
the KDB it doesn't matter, of course, but for the FKDB it does matter because of the absence of Galilean invariance.
Well, in this case, we build it like that, but you can put.
But well, you see, I think that it's very kind of serious difference because when you put both different signs of the initial for the equivalent initial step, you involve this non-convexity feature because MKDB non-convexity has, if you forget about dispersive term, it has non-convex flux, cubic flux.
Yes.
And then you have a whole bunch of new type of solutions that could be very interesting.
Yes, it's yeah. So the zoo is
Yeah, it's
very.
amazing.
Yeah, but I mean, since you're here now, for me, I mean, then we started focusing on this, and I want to maybe let me flash very quickly. I want. So we did the same gymnastic for focusing, and I want to say, so this is focusing. So since you're mentioning it here, so same stuff, and now you can have eigenvalue everywhere, no? For and what we did is to fill densely a domain with soliton. Densely.
to the 2D then.
2D domain. And so you have this kind of Riemann-Eagle problem. So, and so this is for n solitons, so you have this Gj, and this kappa is the characteristic function of this contour that contains all the solitons.
And you feel this domain uniformly again?
I feel now this domain, okay, I feel a domain which is contained by this curve uniformity, so that's the trick. Okay, let's suppose I have a function smooth beta, which interpolates this normal constant. And I say, okay, and then this sum, which is in my Riemann-Eagle problem, I have to scale by n, otherwise I don't have convergence, is equal to this interpolating function. So, and this is the area of your domain. You say, okay, I have a domain of area A, and I say that my norming constant are interpolated by a function times the area. And then I say, okay, this is just an identity. By my definition, take a very nice function. And then this Riemann sum converges to an integral. Okay, so, and the miracle is in this case, okay, you end up with this kind of Riemann-Eagle problem. Say, okay, these are polynomials. But then the magic, okay, so I don't know what to do to it. But then, I mean, this was a crazy observation, but there are some specific value of beta and domains for which you can solve exactly. And the amazing one is that you can even get one soliton solution.
With Marco, you did this with Marco.
Yeah.
Okay.
So, but it's amazingly simple. So if you take beta, just an analytic function, and be a disk, just an exact disk, then you have this integral that you don't know how to do, of course, but then if this is analytic and this is the disk, you apply first grid theorem and then Cauchy theorem.
So the common gas becomes a single solution.
And then you write to this exact formula, and this is the Riemann-Eagle problem for one solid. So that's so with this is, so you calculate this is the Riemann-Eagle problem for one solid. Then so what's the message? So you take infinite number of solitons on a time disk and they condensate to one soliton. So that's the message.
Yeah, we need to see what.
And so the numerics are, okay, let me explain what it is. Let me explain. So what you're seeing, so this is what you're seeing, the expected one soliton solution. And then you have this bunch of stuff that you're sending to infinity because you're looking at it second key, you're sending to infinity with speed log of n for any number of solitons.
Yeah, that's understand. Yeah, then they just go to infinity.
Yeah, but what remains, so there is a tail that interacts constructively.
Tamara, you're saying that the distribution is uniform of the centers and the norming constants, which are encoded by this beta,
It's an analytic function.
just any analytic function.
Yes, an analytic function. And it's, I mean, this is just calculus. Calculus.
Somehow very degenerate is what people is.
It's what it is, yes. And so this is the numerics. So we sample the data with n equal 100 to 100. So it's going to infinity. We took r equal 1. Maybe if I choose a nicer function, I can send this soliton to infinity much faster. But so so the one soliton that is this is the theoretical soliton is coming out already with 100.
I understand. Well, can you see all kind of simple terms again? So you do your deterministic soliton gas. For instance, I mean, you have infinite number of solitons, and they form elliptic solution. Right? In this elliptic solution, you send period to infinity, you get a single soliton. Is this essentially this?
More or less, yeah.
Okay, good.
Yes, because indeed, okay, yes, more or less is because if you don't take exactly, if you don't take the disk, but you take the ellipse as a domain, you see a step-like oscillatory equation. And when the ellipse become a disk, you get one side, which is yeah. But I just want to say that this is was very surprising actually for us. I was expecting to see a less, but yeah. So the only thing is this paper, there is a choice of the density, which in this numerics are equal to 1. Maybe you can better choice to send this state to infinity faster, so that you really see. So because log n is a slow growth. 100,000 to see something.
Thank you.
But many people, other people will speak about it extensively among.
Yeah, of course.
So, Tamara, in naive question on the randomness. So,
There is
if,
no randomness here.
yeah, there is no random. So, as long as if Kali is given nicely, you have this particular realization of what we call a soliton gas, and then you start this asymptotics. And so, when you mention randomness, and you say if random, what do you exactly mean? So,
Well,
how do
you
you know that this particular representation is statistically meaningful, so represents the
Right.
equilibrium of something?
But I don't know, but I mean, it represents, so there are lots of numerical experiments in which Kennedy has done, Deterministic, there are many with random soliton, and we try to do some mathematical analysis of that, but I mean, so at the level of inverse problem, I mean, the mathematics is not there yet. So you want to start the inverse problem with random spectral data.
Yeah, but when you say random, what kind of distribution?
Well, I don't know. For example, in the paper I've seen, I don't know, maybe yours, they take the amplitude between a set and random Gaussian variable, and the phase are maybe deterministic or so.
Okay,
Yeah, but this is very so it's from the mathematical point of view, I'm not able to do much.
This is what we call soliton products.
How do you know that this is coming?
Okay, it's my
Hmm?
It's my hypothesis, but I'm pretty sure. Okay. We will talk. Okay, thank you very much.